Hello, my name is Mark Friese. Today we'll be discussing navigating idiosyncrasies in IoT development. The purpose of this is to really drive home some of the issues we've dealt with and in some of the experiences that I've had with embedded development systems and the issues that you come across in addition to how we've addressed some of them. So there's a little bit of background. It's actually my birth certificate. I've worked with Apache NiFi MiNiFI C++ for about a year and a half. Prior to that, I worked with data warehouse and query systems and had more of a tangential role with NiFi. NiFi was sort of the systems that have fed the systems that I worked on. And before that, I worked on embedded systems where I worked with single board computers for switch manufacturers. And I'll get into some of that history in a bit, but what I'd like to discuss today, going over the agenda, is what MiNiFy C++ is, the use cases, some of those idiosyncrasies, and finally ending with some of the lessons learned. I have sort of an expectation, because I have a lot to cover, that everyone is familiar with NiFi, but the same tenets that NiFi provides, the data flow management, provenance, providing you the data lineage, we try to provide the same thing in MiNiFy. We try to be good stewards of systems. One of the best infographics, I didn't make this, I stole this. In fact, I had a lot more images and they were removed for legal reasons, for copyright, and I tried to tell them that I don't really have a single original bone in my body, but they didn't go with that. On this image, though, on the right, you see the core infrastructure. This is NiFi. This is where we own the box with NiFi. As we move further to the left to the regional infrastructure, we may be receiving data from these edge devices. MiNiFy lives at where the data is created, the planes, the trains, the automobiles, the smartwatches, your smartphones, etc. For those of you who are unfamiliar with MiNiFy, MiNiFy is first and foremost an agent. That is, it provides a lot of key characteristics of this NiFi ecosystem. It has full integration with NiFi, and it's also built upon a library that provides you as the developer the ability to sort of implement these features if you see fit. Before we sort of get into some of those idiosyncrasies, I'd like to just set the stage of, there are many, many definitions of IoT/edge. And the thing that I want to call upon is that with IoT devices, we typically think of these as the data collector, the data sender. With edge devices, we start to open up the world for edge computing. These typically live at the edge of one's network. And in many cases, they're one and the same. There's nothing to suggest that your smartphone can't perform machine learning or that your smartwatch can't do the same. What is consistent across these two paradigms, though, is that there's an explosion of data. So as we get into some of these nuances that we'll discuss, the explosion of data, the increase of data has led us to scalability concerns, and we'll go over how we've tried to address that. Many of these IoT use cases that you hear, I think if you go on the internet and you read all the literature, you'll find a lot of different articles about things that are built upon Raspberry Pi, Arduino, et cetera. But there really is no clear-cut definition of what IoT is. It's just an Internet of Things, right? But any of these objects that feed the clouds or your core infrastructure can effectively be an internet, or a thing on the internet, rather. And as we'll see, I noticed this earlier. There's a light bulb. Again, I stole this image too from this website. I actually gave the source this time. I have Philips Hue bulbs in my house. That means I have a Philips Hue bridge as well. Those devices, if you run Wireshark, you'll see that there's very little crosstalk between the bulbs themselves and the bridge. In that case, the bridge acts as the intermediate, the edge device of your network. And we'll get into how that plays into these idiosyncrasies. Typically, most of these IoT devices feed some core infrastructure. There's typically minimal grooming because you may not always have the capacity to perform some type of compute. So for example, if you're running an FPGA board with a microprocessor, which I'll show a little bit later on from one of my experiences, you can't necessarily send a model to that and use TensorFlow. But in our case, our agent is built so that we can facilitate that and many other use cases. We may or may not have compute capacity at these devices, but when we start to look at the edge computing cases, you start to open up the world where you have devices that have significant compute capacity, robotics, et cetera. There are many different agricultural companies who are building these IoT/edge devices that are on their caterpillars, on their devices that allow them to connect them to the internet or connect them to an internal network. Had a picture of Steve and Tyler here. They said no. The edge processing inherently increases your compute capacity across your infrastructure. So as Forrester said, Forrester alluded to this earlier, where you have all of these edge devices funneling significant amounts of data. But there are a lot of nuances that we'll speak about in a few moments that impact how you're going to do this as a developer. How many people in here write C++ or C code? Okay, handful. So I'll try to tailor some of the discussions to be a little bit general if you're not familiar with some of these concepts. But edge devices can be pretty much anything you can consider. So these have vastly different idiosyncrasies. They may or may not have transient power sources. They may or may not have the ability to perform significant computations, et cetera. So as we get into these discussions of nuance and how we've addressed them in MiNiFy, I'm hopeful that maybe if you're developing your systems, you can take some key takeaways, especially from the examples I'll try to provide where I've really made major mistakes in my career. These use cases, again, I want to drive home the fact that these are the data collectors, the data senders, the edge analytics, the edge processors, and we deal with that typically in our agent, but you can also use some of these same facilities in our library. The first thing that you run into, I think, is, for one, as a consumer of our agent or our libraries, you run into major issues with building. This is because there are so many different devices. Amazon IoT, Azure IoT, Google IoT, all of these libraries provide many makefiles, or in some cases they choose to go with Java or Go, for example. There's nothing wrong with these approaches, but there are many ways in which you can use and run these systems. Our goal with MiNiFy is to have as small of an agent as possible, and also have the ability to give users the flexibility to tailor their binary to what they need. So we've used what I've effectively called, or rather my colleagues have effectively called, the BuildABear approach. This means that as the consumer, it is up to you to choose which features you select for a given binary. This doesn't limit you in any way. There's always the possibility of dependency injection if you wish to incur that cost. There are many different software versions on all of these devices. Going back to the example of Philips Hue, I don't specifically know what they're running on those devices, but I can assure you that if we go back to the previous slide, I apologize, you can see some of the feature sets which we allow or disallow for given hardware. We provide you the ability to do llama detection with TensorFlow if you see fit. You're not going to do that on the Philips Hue bulb. And that seems obvious, but it's not as obvious when you maybe speak to all the different use cases that people want to perform. There are many different operating system variances, of course. We ran into an issue. If people aren't necessarily familiar with C++, there's a concept of ABI compatibility, application binary interface compatibility. This concept, which is effectively just boiling it down to the most simple definition, is that we provide, there may be binary compatibility between libraries. So for example, if you have a shared object, which is maybe tantamount to some injected dependency, you may have, the libraries may function, and the function calls may proceed as correctly, but you may have other issues internal to that library. And we ran into these with Raspberry Pi. We provide OpenSSL support for secure communications. When we did this, we actually ran into issues where we had a seg fault, and this is because despite being ABI compatible, those libraries weren't implemented in the same way across those versions. And there were tons of emails on their mailing lists, to which I'm not a purveyor of OpenSSL, I can't tell you everything that they implement. So this is going to be a constant configuration management problem. The goal here with the agent, though, is for us to build the bootstrapping so that you as a consumer, the developer, don't necessarily have to worry about that as much. I'm currently working on cross-compilation support to facilitate making this as easy as possible to build these agents and these libraries as easily as possible for different architectures without having to know much about them. That's a tall order, but the configuration management onus is on us. And again, many different types of hardware. I think one of the things Forrester called upon was running a very small piece of code on a device. If that's the case, and you know specifically what you want to run, that's great, but in many cases, we want the ability to change what we're running. And as we get into some of the more runtime nuances, one of the things we'll call upon is command and control as a way to continually keep track and update our agents in such a way that we don't necessarily have to worry about the configuration management problem as much. So here's a list. I pared this down from about 20 because I realized I probably wouldn't necessarily have time. There are a lot of issues, I think, that come up. In my days with single board computers, we ran into a lot of issues because there were no kernel modules for a lot of the hardware we were building. We were building custom hardware. We had a PCB facility. And in that facility, I spent a lot of time writing kernel modules and triple resetting those CPUs. That means hitting that trap 3 times, the machine just restarts, and you have no way to debug. Actually, if none of you know this, my Twitter handle is Mr. Segfault. I'm very good at that, if you haven't been able to tell. But many of these devices, we have to be cognizant that many of these data collectors and data senders don't necessarily have significant compute capacity. So for us, we've dealt with this with a variety of ways by ensuring that our agents have the ability to scale all of their internal resources. This comes down to timing, thread pooling, et cetera. And if you have devices that don't necessarily have the ability to deal with this, so if you have devices that are RTOS, for example, we provide those same mechanisms in our library, but it's up to the onus of the developer to deal with them. We also have learned, and I've learned through some poor experiences, that battery management is going to be a major issue, especially with these devices. If you have a device that's running on a car, as we'll get to an example later, you are not guaranteed that your power source is going to be on as long as the car's on. There are multiple different power sources on different vehicles. And I'll get to an example later with the Uconnect system of the Jeep Wrangler where I tried to build a fancy FPGA example for reading CAN bus data and failed miserably. The next 3 items, the restricted software libraries, the being updated, not being updated frequently, competing standards and protocols, those tie into the command and control vision. So we'll get into that in a bit. I don't want to harp on that, but I do want to mention that all platforms have different availability and potentially at different times. Depending on how you build your binaries, if you choose to use dependencies that are built on the system and not necessarily statically build, meaning that you choose to rely on the operating system's repositories for getting dependencies such as OpenSSL or curl, there could potentially be changes in the long run. And we don't, in a binary that's sitting on a car or in a facility that's rarely updated, we want to make sure we can take those concerns and risks into account as we build. The more important thing, I think, is that we ensure we have a consistent command and control vision to be able to update these binaries, because errors and failures will occur. Scalability is another issue that, as I mentioned earlier, I worked on with single board computers and switches for telcos about 13 years ago. That time, we were working on custom test framework to take hundreds of machines that we built on switches, sending data back to our internal repo or internal system for collaboration. The problem we ran into is I told management, hey, this is a great idea, some great command and control stuff that we're doing. Let's try and deploy this to customer sites, and they agreed to it. So these telcos agreed to let us deploy. We'd gather statistics. These were devices with, at the time, we considered significant compute capacity. But as we did that, we sort of exploited a poor design in that our internal infrastructure couldn't handle the amount of data that was suddenly being sent. So one of the points I mentioned earlier, and as Forrester mentioned, which is a very prescient point, as with edge computing, you effectively scale your architecture. You're horizontally scaling because you have all of these devices that can suddenly perform some task for you. But if you're not careful and you don't scale appropriately in your core infrastructure using something like NiFi, you won't be able to take that data. So in our case, we actually failed miserably, and because of the bugs and because we were writing kernel drivers, Ring 0 halted as a result of us locking up our our communication mechanisms. Therefore, our customer switches failed entirely, and we had to go back to the drawing board and redesign a lot of this. The final item before we move on to some of the resource awareness slides is privacy and security. And I put this up here only to make sure that no one thinks I'm putting this off to the side, but I actually am. I think that's a discussion better given by people who are more adept to security and privacy. I am by no means a master, and I think that would be a very large or long discussion. But it's incredibly important. So the first, as I mentioned, many of these resource awareness mechanisms we built in the agent can hopefully be, these lessons learned can hopefully be taken, maybe if you're doing your own development with these libraries. But I'd like to impress upon everyone that battery monitoring, power monitoring is very important because, for one, power sources can be transient. If you have a device that's deployed in the field and it's only on solar, you may not have power for long term. We've dealt with this by throttling mechanisms. I mentioned those throttling mechanisms that we've built into networking and thread pools and virtually every part of our agent. Those allow us to adjust processing as needed. So if we need to slow down anything within the agent, we can do that in real time based upon the monitoring characteristics of the battery. I have a video of this. I think it's posted in the bibliography where this is just running in real time on a Raspberry Pi or a computer, and it'll slow down processing. So if something as simple as if you're running a model in TensorFlow, you can slow down your processing and avoid killing the entire device. Remember, the goal here is to avoid, we need to be good stewards of that system. If you remember that infograph earlier, NiFi may own that box, but as we move to the source of the data, we don't own that device. We're just a very small part of it. Next issue is networking management. Obviously, you as the developer with these IoT devices, you may have access to multiple networking controllers such as LTE, Wi-Fi. We've built facilities to select those based on rules. So if you're in a connected car case and you have a device that's connected to LTE or 3G, you don't necessarily want to send 100 megabytes of data across that. You don't want to be the one to tell management, we just spent an extra $300,000 because these vehicles have suddenly sent a lot of data across the wire on a rather costly networking controller. So the goal here is to select the appropriate networking controller based on the situation. And finally, in terms of resource awareness, you need to be aware of your persistence. So many of these IoT devices, these data collectors, the smart home devices don't necessarily have persistent storage. A light bulb probably doesn't have storage for information. That's why it sends data and receives data from a Philips Hue bridge. In our agent, we've dealt with this in a variety of ways, and this will tie into some of the command and control discussions, but for one, you have to be aware that all of your storage may or may not be persistent, and if it is, it likely could fail. I have probably 20 RPIs at home, and at least 2 or 3 of them have failed due to hardware. That's obvious, and anyone who's dealt with distributed systems, I used to be able to go SSH to a box if it went into read-only mode before Hadoop took care of that gracefully, or HDFS took care of that gracefully. In that time, we had the ability to connect to that box, but in this realm, you don't. You can't just SSH to your box that's on someone's vehicle, for example. That's a very trite example, but IoT and Edge geographically explode the locations of where these devices can be. So durable repositories and, more importantly, repo awareness. And what I mean by that is that we're aware in the agent of the type of storage that exists. So if we need to switch from durable repositories to volatile, meaning that we switch to memory only, or from a write-ahead logged repository to something that's not write-ahead logged, then we can do that automatically. And we can also do that given commands. So in the design that I've linked here, we have a command and control design for our agents that allow people who use the agent, or people even that use the library to some degree, to partake in some of our capabilities. So our design, which lays out some RESTful API calls for a RESTful protocol, mind you, we're protocol agnostic, so we can link across MQTT and hopefully in the future CoAP, OPC UA, et cetera. These facilities provide us the ability to start and stop components, provide updates, to binaries or to what the agent is doing. And by that I mean, if we need to update the binary itself per some requirement that maybe we need to inject some dependency, we can do that. It also gives us full control over the device if we need to. So if we have full disks or full connections, et cetera, we can deal with that gracefully. I think one of the biggest issues we'll probably run across is device failure, disk failure, et cetera. And this allows us to make changes so that if we have a configuration that's storing information to disk, we can change that if need be. To kind of drive home some of these points, I'd like to go over a couple of examples. These examples sort of relay some of the issues I've run across. In many of these cases, I'm going to provide two examples, one of which is the data collector, the data sender. The most common example I read on the internet is connected car. We have all of these systems. It's interesting because not all use cases are the same. I have a college friend who works at BMW, and he was telling me about some of the work that he's been doing with their connected car-edness. And I was comparing it to the systems I've worked on or touched upon, which one of them, namely, is my former Jeep. That's me doing bad stuff to it. That was brand new when I did that. And I gutted the entire interior trying to do some cool stuff. When I sold it, they told me that they wouldn't give me much money for it, but it was a fun adventure. My point about BMW, though, is that they have significant capacity, many gigabytes of memory, 8 cores rather. They have a lot there, whereas my Jeep did not. I don't know the exact specs, but those of you familiar with Jeep, there's a Uconnect system, and that system, while it does have some capabilities, it didn't have very much. What I did, this is about 7 years ago, when I remembered Verilog and VHDL. Now I can't even spell those really. These boards I had two boards. One, I don't know if anyone could see, is anyone familiar with the Vertex 2 chipsets for the Spartan boards? There you go. One lied to me, just put his hand back down. It's okay, you don't have to stay. He's a friend. These boards, they make multiple ones. Most of them have microprocessors to allow C support, but they also have FPGAs. Some of these boards do not have persistent storage. I had two, one with and one without. They had relatively limited processing. The FPGAs could do a lot, but by contrast, you only had a limited amount of FPGA. You couldn't write infinite amounts of code. You only had so many gates. With this, because of that, I had two boards. They were daisy-chained, one with and one without persistent storage. I thought I was being smart. I used UDP as a protocol, and I made up my own protocol there because I didn't have a TCP stack. I didn't have memory to support one. This, to me, is a very good example of what could go wrong, or many of the nuances that you see in the connected car, the IoT use cases. As I mentioned earlier, power is transient. The Uconnect system has three sources of power. One that, and I didn't know this at the time, one that turned off when the engine was off, one that turned on when you took the key out, and another that was persistent as long as there was battery support. I did not use the latter. I actually used the one that shut off when the engine went from start to on. This caused a lot of issues because obviously with UDP and my custom protocol, I wasn't actually able to get all of my data, and I didn't know why. This is my first jump into not understanding the merits of power management, and more importantly, dealing with durable communication mechanisms or durable repositories. So the board that was storing information stored it in such a way that I couldn't read it. I later found out that there was a company that sold a device to do exactly what I wanted for $100 and significantly less effort. Another example I want to go over is a good example. I have a video of where I built a robotic car with a Raspberry Pi. In that car, and again, it's linked there, and it's also on my website, which I'll link at the end. That example is one in which I initially started with using OpenCV to detect red in images. This car had a camera on the front, 3 servos, and 2 motors in the rear. The motors obviously drove the car forward, the servos moved the camera around. The goal of this was to detect red and then move almost like a bull, for example. In this example, I had major issues initially because I was sending the data, or rather sending the images to NiFi. And as people have made jokes, this isn't a real-time operating system. We're not actually, NiFi is not intended to do that because obviously it incurred significant latency. But I just wanted to see what would happen. When I moved the processing, that is the OpenCV, to the device using Minify, I ran into other issues. First, it worked very well, but this device, this robot car, is on battery power. What I didn't initially realize is that as the car slowed down, or rather as the battery drew down, so did the car, because as I mentioned, I'm adjusting resources in real time, slowing down whatever threading we need to, slowing down whatever control mechanisms we need to, and as a result, that actually caused the car to sputter along. Less so than if I just sent the images to NiFi. What I was trying to do here was doing some simple reporting and analysis and send that to NiFi, and then do the OpenCV analysis on the device. This is an unintended consequence, I think, of if you do manage your resources, if you have a device that's sitting on your edge and that's sitting connected to a power source, a consistent power source, it's not a big deal. But if you're connected to some transient power source like I was, which were these batteries, not only do you have to monitor them, you have to deal with the fact that your processing will slow down, and that almost has to be a part of your use case. In this case, I was using a faster persistence mechanism for my data storage, which was not using write-ahead logs, but that actually caused issues when I initially wasn't monitoring the power, and the device just cut off. I then switched to a write-ahead log repository, and it worked rather well, but again, these are things that were more difficult if I didn't have the ability to change the agent through some command and control mechanism. When we look at this, I say what we've learned. Maybe a lot of this is what I've learned. I hope that a lot of this is obvious, and if you're writing your own IoT tools, you're using these open source libraries, I'm hoping that maybe I imparted something from my mistakes, but also hope that you also don't make as many mistakes as I do. Not all use cases are made the same, and I think that's pretty important. What you see on the left-hand side of that is the robotic controller as I was making it, along with, I think, what is a GitHub sticker. On the right, you see a very contrived example, Sense Hat. I was measuring humidity across my house, and on my website I have an example or rather I have an article about that. The one on the right is always connected to a consistent power source. Connected to Ethernet, the one on the left is using Wi-Fi. Has a battery power pack. So these use cases are very different. The one on the right is your typical data collector, your data sender. It didn't need to do much analysis. Even though the Raspberry Pi has significant capabilities, I didn't actually need to do any analysis. The one on the left, it behooved me due to the networking constraints to do that analysis at that device, even at the cost of battery power. So before we get to questions and the conclusion, I wanted to go over some key tenets that I picked up while making this presentation, really, is that, for one, failure is always an option. This means that, obviously, any device that's deployed will fail, especially if it's hardware that you didn't make yourself or doesn't have certain mean time between failure guarantees. As a result, the best way to tackle this, I think, is some type of command and control infrastructure to facilitate having resolution to some of your problems. If you're building your own software, or if you're using our library and you're piecing some of these things together, we provide some of these capabilities to our library, but if you choose to build your own command and control infrastructure, you need to have a way to update your agent's capabilities. This means updating the flow, what it's actually doing. But if you also must be cognizant that updates need to be relatively small. There are many different protocols, as I mentioned earlier, some of them competing in ways for different paradigms. OPC UA, Unified Architecture Protocol that many use in oil and gas, MQTT, all these various protocols all have different limitations, and as a result, it's better for us to be able to minimize what we send and find ways in which we can do that. One of my colleagues has always mentioned Google does a lot of great work with binary diffing, and I think that's a great idea. If you're performing updates to your agents, that's a great idea in order to limit some of the ways in which you have to send all that data. And obviously, just because you have the ability to do something doesn't mean you should. Just because you have features doesn't mean you necessarily should use them. Obviously, more features, more money, more problems, more features, more problems. And I think this is my way of saying that even though you can build, with our software or any type of bootstrap system, even though you can build a relatively small binary or an uber binary, it doesn't mean that you should choose the latter. I agree with Forrester, you probably should choose the tightest binary, the tightest set of features for your use case. Otherwise, you're going to run into issues for dependency management or even binary sizes. It's very common in this industry, especially with IoT Edge, for people to say, your binary is 4 megabytes. Well, great, how much resonant memory does it use? But there is value in having a small binary because it means that you can obviously transmit more of your data, or rather transmit that binary across more of your devices, especially if they're using very lightweight protocols. In conclusion, I think I probably could have just shown this one slide and made, all could just grab some coffee, but if there's anything I want you to take from this is the three conclusive idioms that I can provide are obviously the BuildABear approach, in my opinion, is the best. That's because in Minify, we deal with a potentially innumerable number of devices. If you're trying to deploy your software on a very specific device, you may not necessarily need some of these idioms. But for us, the BuildABear approach allows us to deploy all of our feature sets and future feature sets to as many devices as possible while we figure out ways to cross-compile, deploy to these various architectures, et cetera. And the goal is to eventually take this away from a script and put this into the same flow-based programming that you expect from NiFi. Control your data and resources. This means obviously understand what your resources are and your limitations are, limit them as much as possible, present controls, and control the data that you output. That kind of plays to the scalability concerns where you may not necessarily have the ability to scale your core infrastructure, but you need to be cognizant of that fact that more data, more issues. Of course, you just make your cloud bigger, right? Expect failure. That's the most important thing. Failure will occur. There are a lot of topics I didn't cover, including starvation and separation of these agents. There are a lot of topics, especially in regards to almost sandboxing them, that I likely didn't have time to discuss, but those are contexts that I've dealt with in the past that are really cool about trying to not only expect failure, but deal with it in ways that you don't necessarily have to lose your data, because you can sandbox it and isolate it in some way. But to get there, you need to have a command and control infrastructure. You need to be able to control your agents, control your binaries. In reality, we're not all going to deploy on Raspberry Pis. That's a very simple architecture, and it's also one which is less constrained than what reality presents. But my hope is that you can see that in Minify, we've taken a lot of steps and learned from a lot of lessons, and I'm hoping that you can potentially learn from them as well. There's my contact information. If you have any questions, feel free to ask. Yep. Oh, wow. I don't know if I can actually say a best way. We're working on ways in which we're dealing, obviously it's useful to have some type of device registry to know what your devices are. In our case, you can look at our command and control infrastructure. We have a heartbeat protocol that allows us to build somewhat of a device registry. I can't speak to what's the best way, but I think there are certainly a number of different strategies that can be done. It's really hard for me to say a best way because it really depends, on where are these geographically located? Are these going to be built and sent from one facility? Are these going to be accessible over the internet? Is this going to be a private network? There are a lot of caveats. I'd be happy to kind of discuss that. You know what? Anyone that asks a question gets a NiFi sticker. I have a bunch of them, so even if you don't ask a question, you get one. Here you go. Go ahead.
You mentioned earlier command and control, and maybe I get Miles
I think as I'm going to leave that as yes, and primarily because obviously there are some things that almost as a vendor head, I don't necessarily want to discuss everything, but yes. So there's a larger vision at whole, and there are things that we're building that we'll build into that. There's a lot there, so yes. Maybe we can have some further discussions, but there are going to certainly be cases where all of that will play into it, and we're currently building a lot of that, and some things I don't know what I should and should not discuss. Any other questions? It could be. Mm-hmm. So we do have an example of one of my coworkers building an example where he showed how we could detect cats on a Raspberry Pi using TensorFlow, and that's certainly part of this what we're building, and what I think others are building as well. You can't necessarily expect to send that model across the internet and send it to every single device. That may not be possible. But in many cases it could be, and there are different complexities with like peer-to-peer architectures that we may be able to use to get that model to those devices. But yes, that's certainly, while power was maybe a big part of this, again, that was kind of in the interest of time. There are a lot of concepts that you could perform. We have TensorFlow processors that allow you to send a model to your agent and then run them and get certain things like labels, et cetera, and extract labels, for example. But we're sort of a general framework. We allow that use case and many others. And that is certainly something that we're considering and we're thinking about, because there are different caveats in that case. And those caveats could run the gamut of, obviously, battery power, but also we don't know what other things are occurring on that device. So that's some of the work that I'm looking into, which is monitoring not only ourselves, but the rest of the device, to ensure we don't conflict in some way, because the systems that that control the propellers, et cetera, those are more important than us looking at imagery, for example. So there are a lot of caveats there that I wish I could have gotten to, but 40 minutes, I'm afraid there wasn't enough time. But again, happy to discuss afterwards. Anything else? About a minute and 20 seconds. And here's the bibliography. Feel free to click the screen. All right, appreciate everyone coming. Thank you very much.